This is M1, section 16, moment of a force, on page 51 of the M1 notes booklet. As usual, this is a video, not a normal lesson, so you may need to pause in order to take notes. Right, so in this instance, you've got a seesaw, and there are two children, or balls, at equal distance from the pivot in the middle. Then the heavier child will basically make the seesaw go down. That's because he presents a greater weight on that side. But if we wanted to balance, we would need to move the heavier one nearer to the pivot. In that case, it would add less turning force around the pivot. So basically, the closer to the pivot, the less capable a particle is of turning body on which it's acting. And the main example of that is a door. So here's my simple door model. I'm going to use a calculator. So I've got my calculator. Now our door handle is on the opposite side to the hinges. So, and as you can see, the calculator is easy to turn as I do that. Now if I try to push at the hinge, it becomes very difficult to move it. But easy on the other side. So the further away it is from the pivot, the easier it is to turn around the pivot. Now, the moment of force is a measure of that turning ability, a measure of its capability to turn the body on which it's acting. And like in a lot of mechanics, it comes up with an equation. So the moment of the force, F, about a point P, is equal to the magnitude of the force, F, times the perpendicular distance from the point P to the force F. So in this simple case, where we've got a perpendicular distance, perpendicular being right angled, then and I've got my force F, then the moment is just simply F times x. In this instance, if the distance I've got is actually at an angle and not perpendicular, then a bit of trigonometry will give that the perpendicular distance is d sine theta, and that the moment is the force times d times sine theta. Now in M1, we'll be mostly focusing on these particular calculations rather than those calculations, but you still need to be aware of them. Moment, being force times distance, is measured in Newton meters. Newton for force, meters for distance. Now moment can be clockwise or anti-clockwise. So in this, it depends how it turns. So I put my finger on the point personally, and I turn the force as if it was going to go round that point. So in this case, it would turn in an anti-clockwise direction. Similarly, with this force, just same one on the other side, if I was to turn it round the point, it would go like that, and it would be a clockwise direction. Now, in this case, light rod AB is 6 meters long in a vertical plane about a fixed point C where AC is 2 meters. So these drawings don't need to be to scale. We often draw pivots like as a triangle, and then 6 meters all the way, so C to B must be 4 meters. Now we've got a vertical force of magnitude 10 newtons acts in a direction perpendicular to AB. I'm going to have it pointing down. It's not been specific in this case, but we'll have them pointing down. An example would be more specific. Calculate the moment of the force F about C when F is applied in 3 different places. So in part A, it's applied at A. In part B, at B. So we're going to label the forces in the part, and at part C, C. So dealing with A, the moment is force times distance. So in this case, in each of the 3 cases, the force is 10. what we need to do is the distance. So we are doing the moment about C, so the distance needs to be from the point C. So in this case it's 2 metres away. So 10 times 2 is 20 Newton metres, and if we turn the force around the point C, it would turn in an anti-clockwise direction. For part B, we'll write the equation again. The moment will equal the force, which again is 10. And now we've moved the force to part B over here. It's now 4 metres away from C, so 10 times 4 is 40 Newton metres. And if we spin it round, it spins clockwise. Finally, in part C, the force is acting through C itself, so there's no distance away. So the turning force is 0 Newton metres, right on the pivot, you can't turn it. So you don't need to put anti-clockwise or clockwise, it's not turning. Example 2. Now very often we need to do the sum of moments. Now when we're doing the sum of moments, I like to draw a table for it. So force, moment, now we're doing the forces, the moments about A. Now there are 3 forces, 4 Newton, 2 Newton and 7 Newton. Now the 4 Newton force is, it goes through A, so there's no distance away, so 4 times 0 equals 0 Newton metres. Direction doesn't matter when it's 0. The 2 is 3 metres away, so 2 times 3 is 6 Newton metres, and if I spin it round A, it will spin in an anti-clockwise direction. And then finally the 7 newtons, 3 plus 1 is 4 metres away. So 7 times 4, 28 Newton metres. If we spin 7 newtons around A, it would spin in a clockwise manner. So when we did the sum, we have to take into account that anti-clockwise will cancel out clockwise. So maybe adding, but we'll start with the biggest. 28 clockwise minus 6 anti-clockwise will give us 22 Newton meters clockwise. So they can't balance out. So the total is 22 Newton meters clockwise. Example 3, got several different types here. But again, best thing to do is the table method. So in this case, 2 forces, 4 newtons and 1 newton. And then we can do the sum. So the 4 newton force, both these distances are perpendicular. So 4 times 2 equals 8 Newton meters. And it spins in a clockwise direction. For the 1 newton, it's 6 meters away, so 1 times 6 equals 6 Newton meters, and in this case both the forces spin clockwise. So being both in the same direction, we add them together, we get 14 Newton meters clockwise. Part B will be a bit harder. So we can find our perpendicular distances first. So we want the perpendicular distance from O to the 5 Newton. Because of the trigonometry, that's 4 sine 30. Which is equal to 2 metres. Again, do the table. Two forces, 5 newtons and 4 newtons. So the 5 newton we've worked out to be 2 metres away, so 5 times 2 is 10. And that would spin in a clockwise direction. The 4 newton force, we've extended line of action. So the perpendicular distance is 1 metre, so 4 times 1 is 4. And if we spin round O, it is also going in a clockwise direction. So do that again. Spins round. So 10 plus the 4 is 14 newton metres clockwise. So directions are important to make sure we know if we need to add them or subtract them. So again, draw our table, no trig required here. So we've got two forces, 4 newtons and 3 newtons. So the 4 newton force is 5 metres away perpendicularly. Both these distances are perpendicular. So 4 times 5 is 20. And it would spin in a clockwise direction. The 3 is 3 metres away, so 3 times 3 is 9. But in this case, it would spin in an anti-clockwise direction. So they're spinning in opposite directions, so we take the largest, 20 clockwise minus 9 anti-clockwise, gives us 11 newton metres clockwise. Final example. So a little sketch to help. We've got a grid, we've got the origin at O. We've got a force 6 plus 3 newtons applied at point A, where A has position I plus 4j. So 1 across, 4 up. There's my point. And then our vector goes 6 across and 3 up. Now in this case, it's probably best to consider it as being two forces acting on that point. The 6i force going right and the 3j force going up. Otherwise you're going to have a very difficult time finding out what the perpendicular distance for the origin to that angled vector is. But it's actually fairly straightforward to find the perpendicular distance to 6i and the perpendicular distance to 3j. So instead we can do it as a sum of moments, splitting the one force into its two component forces. So force sum table. So we've got basically a 6 newton force and a 3 newton force. So the 6 newton force is basically a perpendicular distance of 4, so 6 times 4 is 24. Newton meters, and the 6I force would rotate clockwise. Then the 3 Newton force, again, extend the line of action, it's perpendicular there, so it's 1 across, so the perpendicular distance is 1, so 3 times 1 equals 3 Newton meters. And if we spin that force around, it would spin the other way, which is anti-clockwise. Add them up, and the sum of the moments is the same as the moment of the individual force. So 24 take away 3 is 21 Newton meters clockwise. We get biggest minus smallest if they're opposite directions. So that's part A. Part B is a similar sort of idea, but instead of doing it around the point O, we're going to do it around the point B, which is 2I minus J. Well, point B is there, so the distances will be different. And therefore the moment will be different. Pretty much the same setup, so 6 Newton force is now 1 plus the 4, 5 away, 6 times 5 equals 30 Newton meters, and that would spin round B in a clockwise manner. A 3 Newton force, well it's still 1 away, but B's on the other side of it, so from 2 to 1 is 1, so we'll extend that down all the way there. So 1 across to the line. But this time, because the B's on to the right of the 3J, it spins in a clockwise manner. So both in the same direction, so we add them for the sum. We get 33 Newton meters clockwise. And that concludes this session.